Okay, let's talk about the Bohr model of the hydrogen atom. Now, the Bohr model is sometimes called a planetary model because in the Bohr model, electrons are going to orbit the nucleus like little planets, okay? Electrons are going to be able to move from one energy level to another, and they do this by the absorption or the release of energy. So we'll absorb some energy, we'll jump up to another level, we'll hang out there for a while, we'll drop down to another level, and then we will emit that energy, okay? And so we emit this as radiant energy or light. So what does it look like? Okay, so I've got all these different energy levels. Now, the colors on this particular diagram are just there to help you differentiate the circles. Because sometimes looking at a whole bunch of concentric circles that are the same color makes your eyes go cross-eyed. And so the colors here have nothing to do with anything. They don't correspond to any of the line spectra that we're seeing. They're just simply there to make it easier for you to differentiate between the different circles, okay? So these N numbers, this is what we call the principal energy level. Okay? And so I have all these different energy levels, 1, 2, 3, 4, 5, 6. So electrons will be on an energy level, okay? And then something will come in, it'll jump them up, and then they'll hang out, and then they'll drop back down. And what does that look like? Okay, so I get some energy that comes in, I get some excitation, my electron is going to absorb, and it's going to promote to a higher energy level. It'll hang out there for a while, and then when it is done, it'll drop back down, and it will emit light that corresponds to the energy that it had absorbed, okay? So again, on this model, okay, electrons are hanging out, orbiting around the nucleus. Okay, when we're doing this excitation and emission, you remember that we have this law of conservation of energy. What goes in is what comes out. And so if I have something here in my N equals 1 ground state, and for this particular model, it takes 984 kilojoules per mole to excite up to energy level 2. Okay, so it'll excite up to energy level 2 if I get that 984 kilojoules of energy. It'll hang out there for a while. When it's done, it will emit 984 kilojoules per mole. So I get my, okay, is what I'm going to absorb, and then I'm going to emit out 984, and so my net will equal 0, okay? What I pulled in is what I take out. And so all those different lines that we see from our line spectra are due to these transitions. So we know for hydrogen that the red line comes from dropping from energy level 3 back to energy level 2. We know that the blue-green line is energy level 4 down to energy level 2. And we know that the violet line is energy level 5 down to energy level 2. Okay. Now, the nice thing about hydrogen is it's really simple. So when we look at some of these models, a lot of things are done on hydrogen because hydrogen is simple. Hydrogen has a single electron. And so we can do a lot of modeling because once you start adding in even a second electron, things get really, really muddled because now the electrons are interacting with each other as well. And so hydrogen's a good model. There's something called the Rydberg equation that we can use for hydrogen to actually predict the wavelengths of these different line spectra. Again, it works for hydrogen. We're not going to go over the Rydberg equation in this class. You will go over the Rydberg equation in 141 though. When you start going into a lot of this stuff in more depth than we're going into it right now. Okay. So the thing is that we've got these discrete energy levels. Okay. In our next video, we'll talk about what that discrete energy level means, and we'll talk about something called quantized energy.